Hi everyone, are you able to hear me and see my screen clearly? Great, great, great to have all of you in the session. Should we start now? Hi Abhinav, hi Balaji, hi Bintao, hi Kamal, hi Nirav, hi Noor. Good to have you in the session. All right. So yesterday, the recordings that we did, the audio quality did not come out well because it wasn't through the headphone. So in case you hear a bad audio, a little bit bad audio than this, please make me, uh, please let me know, because sometimes it automatically selects the instead of selecting the headphones audio, it selects the laptop's audio. So that's what happened yesterday. All right. So great to have all of you in the session. We are at a very interesting part of our discussion. All right. So before we start, do you have any questions? No questions? All right. So yesterday we were here. What we had done was this was the confusion matrix visual representation. This was confusion matrix visual representation. And we realized that it's not good enough to present it like this. And therefore we removed the false positives, sorry, true positives, and make standardize the rest of them. And here, after normalizing per row, this is how it looked like. And then what we had was we basically were comparing what happened. So those who did not attend yesterday's session, so what we did yesterday was, from the MNIST database, we did the multi-class classification. Okay, multi-class classification here, sorry. And right, so let me just show you very quickly what we are talking about. So we talked about the performance analysis, then we talked about multi-class classification, whereby if you want to identify multiple things, like in our case we identified multiple digits. And earlier we only did 5, not 5. And here the there are two kinds of strategies, one versus all and one versus one. Okay, one versus all is that we design 10 classifier, which classify a particular record against all others. While while the OVO, the one versus one creates all possible pairs, okay? Not ordered pairs, unique pairs, so that it's like basically total number of handshake between n number of people, okay? So, so if there are n people, how many total handshakes would be? Unique handshakes would be. So that's the number of pairs. And so basically we created those many pairs, those many classifiers, binary classifiers, and then And then we talked about that by default it is OVA. So in our case, in our multi-class case, what we did was we uh, did the we basically used the OVA, because by default the stochastic gradient descent uses the OVA. Then when we plotted it, the whole diagonal was kind of bright enough, and there were some parts which was little darker. Now, then we removed the diagonal, as in we removed the true positive and compared the one where the errors are. Okay, by kind of standardizing the values, meaning averaging out their values and kind of plotted them relatively. Okay, then those differences, those errors in other identification became significant. Okay, so we were able to afterwards see that there are quite a few errors that are happening here. Okay, so here we observe that eighth and ninth digits also had the full columns being identified wrongly. Okay, and 3 5 and 5 3 are abnormally bright. Okay, so the possible solutions that we discussed was gather more training data for the digits that have more confusion. Okay, if our classifier is getting confused between those digits, gather more data. Engineer new features that could help the classifier, like number of loops in an image. Okay, so um, here basically the mm, okay. So here we could pre-process the image and try to identify the number of loops in the image. Okay, and we put it down. You okay? All right. Number of loops, as in right now, if you take a look at this, let me just oh, what happened here? Okay. Okay. So I want to describe something. Let me pick this. Wonderful. Okay. So when I say loops, if you take a look at say 3 and 8, right? Ideally, there are supposed to be here there are two loops, while here there are not. Okay. Similarly, if we could identify in some quick way such kind of thing, then it would improve. Okay. So, all right. So, basically, engineering more features would help us. All right. So we could also do pre-processing of image so that the images are well centered, as in the padding on the left, padding on the right is equal, and they are vertical. All right. So there are out of the box functions available in for doing this in Scikit image, pillow, or OpenCV to make the padding equal on both sides, make the image centers vertically as well as horizontally, in other words. And and one more thing that the pixel densities is something we had normalized earlier that has immediately have an impact. So that was an example of pre-processing image. And okay, so here, you remember this part? Here we had used our standard scaler like we did in end-to-end project. So we fed our data to the scaler, and it basically um, normalized our values, right? So it converted converted all the values. It basically scaled all the values. Okay, so the extreme values or the lower values um, were averaged out so that the overall identification of the 5 and 3 or the characters or any digit became really good. Okay, so there was a huge improvement at this point. Around 4% of improvement is what we got. Okay, so 4%, for not 4%, more than 4%. It would be 4 by. It would be how much? Right? This. Um, okay. So if we had this, okay. So around, yeah, around 4%, 4.5% actually. Okay. So you can see that clearly that it is by pre-processing your image actually does a lot of magic. Okay. So it was just a simple standard scaler which actually improved the values. Similarly, we could use these out of the box libraries to make the padding equal on both sides. Okay, on all sides actually, the make it properly centered, right? And we must analyze the individual errors. Okay, we must analyze the individual errors. Say, for example, we would like to analyze the individual errors in 3 and 5. Okay, so if we draw the confusion matrix of 3 and 5, this will look like this. Okay, and I've just added this piece of code. Okay, so here. All right, those who want to plot, I'm just copy pasting the code here, and okay, maybe I could just push it. All right. Yes, I have pushed it also. So what you see here is here we have first okay, before that you have to define this function. Okay, so before we design here we have created an extra function called plot digits. What it does is it basically, okay, it basically plot a digit properly. Okay, it basically plots, I'll show you, where are we calling here. We're calling plot digits, and we are passing it the um, what was it? Okay, so here it is. So we are saying y train equals to either 3 or 5. Okay, okay, so we are just extracting these two. Okay, we are just extracting all those, and let me be very, very specific. So we are saying that either the train was 3 and predicted was 3, or train was 3, predicted was 5, trained was 5. If the training, so basically we picked all those records where either on the left, whether left and right had 3 and 5. Okay, we only picked those records, and then we basically just picked first 25 records from this. We just picked 25 records from both of them and plotted it. Okay, so 5 by 5 matrix is what we have plotted it. And the plot digits does that. Given a set of images and number of rows we want to print, it does that. So we picked five rows, and we also said this. So this looks like a confusion matrix with various digits. Okay, so here on the left hand side is where actual was 3 and predicted was also 3. On this one, actual was 3 but predicted as 5. Here it's actual 5 and predicted as 3. Okay, so you can see that this is you can see this is actually these are actually, this and this are actually wrong ones, while this and this are correct ones. Okay, so these were classified as 3, these were classified as 5. Okay, so in some of the cases, it's actually very confusing for us also. You can see this one, right? If this digit is given to me, I will mark it as 3, not 5. Okay, and this side, yeah, this one you can see, if it is given me in isolation, I'll generally mark it as 5. Okay, so yes, so our algorithm is not all that bad. Okay, just there are these few corner cases, and yeah, the other thing we could do is right now what we do is we basically give each pixel equal value, right? Each pixel equal value. We could basically assign some kind of a weight for each pixel and calculate the total score for a particular class. Okay. Yeah. So you can see that this is actually 8 and it's actually 3. Okay, but it was able to identify this as properly 3. Okay. Yeah. So okay, so this is another technique that we could do. We could basically, instead of just considering all the pixels just like that, we could assign some kind of a weight and then see the output. And since 3 and 5 differ by few pixels, the classifier easily get confused, right? This loop, one line here and one line there, that one we talked about yesterday. Okay. Again, so we talked about two possible solutions to this. Two possible solutions. Let me just go back. One is pre-process your image. Pre-process your image. Okay. No, okay. Pre-process your image to make it either properly, make it centered, make it completely vertical. That's pre-processing. The second thing we could do is we could assign different weights to each pixel. Okay, and see the results. Third thing we could do is gather more data where the confusion is more. Okay, say for example 8 and 9 case. So that's the conclusion. So, and take a look at the individual errors closely so that we would know what exactly is going wrong. Okay. And the third part was we again pre-process the image and engineer new features like number of loops. Okay. So these were the conclusions, and we won't be going into individual solutions right now, but you can give it a shot, try to improve the performance by using either of the techniques. Okay. Say, for example, trying your hand on Scikit image, Pillow, or OpenCV will make you more comfortable with processing the images. Okay. So I think you can start with Scikit image in your own time whenever you want to experiment, and then things will then you can figure out that a lot could be done on the images. Okay. All right. So that was okay. So this is what we have done till now. We did all of this. We divided the data set, trained it, tested it using Crosswell, and we haven't tested. Okay. All right. Noor's suggestion is that, okay, let me just make a note of it. I'll just keep this in mind. Okay, and notes, 14 January. All right. Okay, so we basically tested using the sum digit. Okay, not the not the whole test data set, and then we did the performance metrics, improved the model using error analysis, and so on. Okay, and we also learned these parts. Yes, that's right, Ross. This is like a hello world problem for neural net. Okay, so what do we do next? What we are going to do is we are going to do multi-label classification and multi-output classification. Okay, let me also make a note of the yesterday's one of the things which we discussed. Thank you, Gopi, for reminding. Okay, yeah, we'll do this over the week. All right, great. Now, the next problem in the classification is multi-label classification. Okay, so far what we have done is we have done multi-class. Okay, multi-class means there were multiple on the right hand side there were multiple different values. Okay, there is one image that need to be categorized into either of the classes. That was multi-classes. Now, sometimes we want to do multi-label, specifically in the case where there is single image and we would like to put multi-labels on it. Okay. In earlier case, it was one-to-one mapping, right? In multi-class, it was one-to-one mapping. Here, it is one-to-many. Okay, so in multi-label, we want to put multiple labels on an image. Okay, say for example, here there is an image here, there is an image here, and we want to identify whether there is Bob, Alice, and Charlie in here. So there will be three three faces that we want to. There are multiple faces that we want to identify here. So there are two classifications in the same image. Okay, there are three actually. There are three classifications in two. Okay, here basically for each of them we are trying to identify. Okay, so So using classifier, we want to put a identify the multiple labels. All right. So there could be one, two, or more such classifications. Okay. A question from Gopi: is the true false the output of testing all three questions? Yes. Okay. There could be a scenario. There are um, this could be true, this could be false, this could be true, and so on. Okay. So basically, we have on the right hand side the y, the small y, is going to have an array of booleans instead of a singular value. Okay. The right hand side is going to have an array of booleans instead of a single value. Okay. So this is called multi-label classification. So for example, what we are going to take is a very simple example whereby we are going to identify in the same MNIST database whether an image is large or is odd. Okay, large and odd are two labels that we are going to put on our data. Okay, large and odd. Large as in 7 or 8 or 9, odd as in 1 or 3 or 5 or 7 or 9. Okay, so each digit could be large or small. Each digit could be each digit could be odd or even. Okay. Uh, Question from Gopi is, so it is like or condition. It is like or condition, not and condition on all three tests. Okay. You can say that or condition, not and condition. Okay. It's like or condition, not and condition. That's right. That's right. So yes. So training data would basically have the information about both the things. Okay. So on the right hand side of so on the left hand side is capital X, and on the right hand side is small y. Small y would be an array of booleans representing whether a particular label is available or not. All right. So let's take a look. Let me go down here. All right. So here we are converting y and y train. Remember what was y train? Y train was the right hand side of the values having the labels 0 to 9. So we are saying we are creating the first column by saying y train large equals y train greater than equals to 7. All right. So this will be a big array, a big series. This will be a big series of Boolean, as in the true false values, and this will be another big series of true false values. So this one represents how many, which ones are big, and this one represents which ones are odd. Okay, so what we are doing is each value is being divided by 2, and the remainder is compared with 1. Okay, so then we are concatenating these two series in the output. Okay, so you can see this is basically we are concatenating them. We are creating a NumPy array such that this is the first column like this. Okay, and this is the second column. All right. Yes. Okay, let me show you. Had it been say x equals np dot array, and let's say we call it first row. First row is, let's say, how should I write? Let's say A, B, okay, and Y is np dot array C and D. Okay, so these are our X and Y. I'm sorry. Okay, I think we'll have to put numbers. Let me just put numbers, not the what am I doing? Okay. Okay, so let me just convert this into I think this will make more sense to you. All right. So is it clear now? 1, 2. So 1 is here, 2 is here. Okay. So it basically first record became 1 and 3. Second record became 2 and 4. All right. As in second row. That's what we are doing here. So we are computing the value for large and the value for odd, and then we are concatenating the columns. Okay, so this is one column, this is another column. That's what we have done here. Binda, is it clear? It's not transpose. It's not transpose, it's just concatenation. Okay. So if you say transpose on this, okay, then it would be like this. Okay. So if we are appending these two as a row, then we can transpose it. We can transpose the transpose like this. Okay, never mind. Good. So if you were appending them like rows, and then we would be transposing it. So in that sense, you could think of it like that. Okay, good. So what we have is we have the multi-label, Y multi-label, having for every record on the left, we have this array containing two labels. Okay, the first one representing last, second one representing odd. All right, this is what we have done just now. Okay, so we had already divided the data set earlier, so we're going to use the same one. Okay, now is the time to do the training, as in we need to do the training. For the multi-label classification, we generally use the k-neighbor classifiers. We generally use the k-neighbor classifiers, and yeah, we'll go into further more details, okay, when we talk about training models. So here what we're doing is we're importing the k-neighbor classifier, and the k-neighbor classifier also has the same fit method, and this is where we are training them. So notice that on the first argument is the usual x underscore train, while on the right hand side it is y underscore multilabel. Okay. All right, I think we did not execute this. All right, so it is doing the classification. Okay, so let's predict some digit. Okay, so for 5, the sum digit 5, it has printed false and true. So it's not big, but it's odd. Okay, so it is kind of working fine. Okay, it is kind of working fine. We can further do the performance analysis. We can further do the performance analysis. First, we use the cross-val predict. Okay, so this is where we are running the cross-val. It's going to take the whatever algorithm we are passing, it's going to train it on 1/3 of the data at a time. And not for 1/3 of the data, it's going to convert it into 3 folds. Okay, basically break it down. It will train on 2/3 of the data and test it on 1/3 of the data every time. And this is what it's going to do. All right, so these 2 lines look, yeah. All right, so in this case, let's take a look at the F1 score. All right. Okay, I need to figure out the average. One is the normal average, other is the weighted average. Okay, so yeah. All right. All right. This is the usual macro average, and this one is the weighted average. And yeah, the weighted average is probably the, yeah, I think I'll just review this after a while. So weighted average is something where we provide the weights for each individual pixel and then compute. Okay, so I need to, yeah, this is something I would like to review later. All right. So yeah, so basically the 2 different kind of averages is a function of your project requirement. In one is using the normal macro one, other could be based on which one do you want to give priority to. Okay, which one do you, because here there are 2 values to compare, correct? There are 2 values to compare. There's not a single value to compare. Therefore, if you want to give more priority, if you want to give more priority to one of the columns, right, then you could give that priority here. Okay, by weighted, as in if each individual element plays a bigger role, then we would like to go for the weighted one. Okay, so okay, let me say it again. Since we are going to compare the results and the results are an array, right? If let's say we got large and odd and the actual one is large and even, right? So we can't really, the way we compared earlier for our confusion matrix, what we did earlier was we basically compared true and false. It was straight. But if we want to compare this with something else, we need to compute. We need to compute some kind of a single value out of these 2, right? Single value out of these 2, and that's where the average comes into picture. That's where average comes into picture. So macro average is normal average, this plus this by 2. Okay. The the weighted average is where we assign 1 to this, 1 as a weight to this, and 2 as a weight to this, and then we multiply and sum it up. And based on that, we compute our F1 score. All right. All right. Did it make sense to you? So internally, this is what it is basically. Internally, it is assigning the weights to the individual one. Okay. All right. Let me just see the average function. How much weight does it assign by default? Okay. All right. So calculate the matrix for each label, find their average, and weight it by the support, the number of true instances of each label. This alters the macro to account for the label imbalance that can result in an F1 score that's not between precision and recall. Okay, so here you can see that um, this is the usual weighted one, and here the weighted one is what it does is it calculates the matrix for each label and then find their average. Okay, so first of it basically would compute the matrix for each one, and once that is done, it will find their average, then weight it by support. Okay, the number of true instances of each label. Okay, and then like the way we compute weighted is we multiply it by number of instances, and then basically right calculate the matrix as in it computes the right. So for each label, it coming back here, I'll show you. Right. So, all right. So this is our Y train predicted. Okay, it's still running. Let it finish. Okay. And so metrics as in it'll basically compare the values. Okay, it'll basically for each value, it is going to compare the values and then compute that confusion matrix for each label. Okay, it will compute the confusion matrix for each level, find the average value of all, and then find their average, which is weighted by the true instances of each label. Okay, that's basically, how should I say, instead of computing a plus b by 2, it's doing a into n plus b into m by 2 by m into n. That's what it is doing. Okay. Let me try to describe again in the context. Let it finish first. I'll describe. Okay. All right. Okay. So we'll I think a better would be I'll just put it in my notes. and we can discuss it at a while later. Let me get more clarity on the weighted one. Okay. The sole idea which I understood is, as per my understanding, is that since there are multiple values to compare, instead of we could either just average all the values, okay, or we could find total number of instances of each of the value, and then based on that we multiply the individual value with that total number of instance and then sum it up and divide. Okay, so that should give you better results. Okay. Right, it is taking too much time. Do I need to interrupt the kernel? Is it taking unusually long for all, or it's only for me? Okay, I'm just putting this note here. Okay, so we'll review it again at later point. As in, we'll just understand how exactly the weighted works. Okay. Should we move on or should we wait for this one to finish? Yeah. Okay, there was one question from Kamal. Why could we not consider this as three different questions? Okay, two different questions. Okay, why mix them? All right. Okay, so all right. Here is a question from Kamal. Question is, why couldn't we have it like two different training sets? Okay, as well as two different training problems. Okay, anybody? So we could actually first trained it for even, trained it for odd, and then predict the two. Okay, predict the values. So yes, that's right. So basically, it is the way we did OVA, the algorithm is actually doing the same thing. Okay, the algorithm internally is doing the same thing. Okay, so the way we built OVA by using the binary classifier, in the similar way, it also creates multiple classifiers and does that internally. Okay, does that internally. So yes, and some of the algorithms also have a slight bit of more optimized approach for these. That's right, Ross. Basically, KNN example with numbers instead of iris. Okay. All right. We can use this as well for the same multi-label one. So we take an image, we first mark it as even or odd, then we take the basically we create first model, first classifier to classify a particular image as even or odd, and similarly we create another classifier to classify it into large and small, and then we feed the data here. Okay, we basically do the individual analysis or do the analysis together. Okay, so some of the algorithms would be doing the same unless they are optimizing at certain point. Okay, all right. So I think there's some amount of time that's going. I think let me come back to this part again. Probably it's going to take a bit of more time. Let it run while we discuss the multi-output classification. Okay, I just hope that it finishes by then. Should we go move on? Kamal, was I able to answer your question? No. So there is another example called iris. Iris is the identification of um, the the flowers, and they're basically we identify the flowers. Okay, so in an image there could be multiple flowers or multiple things, and that's where the multi-label classification comes into picture. Okay, yeah, yeah, iris is also used as like beginner example with the classification. Okay, good. So a question from Kamal is, can I just say that by using multi-label classification, we are just saving few lines of code by combining the two classifications together? So not only code, there are a few more things, because see, when we are processing the data, right, same records are going to be processed again and again. If we are doing that twice, it might take a longer time. As compared to the optimized approaches, some of the algorithms such as KNN, K nearest neighbors, uh, have a better performance than running it. Uh, if you run it in a single shot, both of the on multiple labels, the overall performance will be better. The time taken will be smaller. If you run it individually, if you create a normal single label classifier, as in multi-class one, then it is going to be taking more time if you take that sum of the total time taken. So that's why we are generally combining the two. Okay, so yes, so it's basically for the minor performance gains, and mostly you can do the same. Okay, as in you can also run it individually. You can also run it individually. Okay, so every time you have to predict, you will have to call predict twice on both the models. And similarly, while we have to train the model, train the classifier twi twice, once with one label, second time with another label. Okay, and most of the work is being duplicated internally. All right, so that's one of the reasons why we have a separate thing called multi-label classification. And multi-label was actually solved initially using the standard approach, the multi-class approach. Okay, and it's good that we should always keep this in mind, that multi-label could be broken down into multi-class at any point. Okay, great. Now there is something very interesting one called multi-output classification. Okay. A question from Gopi before we proceed. With multi-label, if we are analyzing each individual error, is it feasible when there are huge number of labels? With multi-label, if we are analyzing each individual error, is that feasible when there are huge number of labels? Okay, so as you increase the number of labels, the complexity of the overall algorithm increases. But it is possible, and it's a function of the kind of data we have. So I'm coming to the very interesting example here. I'm coming to the interesting example where we're going to have 784 labels. We are going to have 784 labels, and that would help you. Okay, there in this example, the one that we're going to solve, they're going to be huge number of labels, and I think that would answer your question. Okay, a question from Kamal: Google Photos or Facebook identify the people in pics, is it also multi-label classification problem? Yes, because it identifies people from so many different people I know. Yes. Okay, so it's basically it's multi-label because in a photo there could be multiple people. Okay, had there been, we knew that we are going to have passport size photos and they're going to be one person, we just want to identify one person. In that case, it could have been just multi-class. Okay, and the various classes are going to be multiple people. Yes, go ahead, Noor. That's right, Kamal. So first, what it does is it first identifies that if basically there are uh, persons in the image. Okay, so instead of only detecting or recognizing friend, it recognizes whether a photo has a person or not. Okay. Okay. With multi-label, okay, let me read Gopi's question again. Gopi's point was, okay, thank you for bringing that. I missed some part of it. With multi-labels, if we are analyzing each individual error, is that feasible when there are huge number of label? In this case, okay, okay. So in our case, yeah, you are right. Thank you, Noor. So in our case, the one which we have taken just now, there were two labels, okay, odd and even. Basically, there were two labels, odd and even, for each of the image, okay, each of the image. There were only two labels. All right, I think Noor is right. Yeah, that's right. Okay, so okay, in case of multi-class, we had 0 to 9 as the class, right? And in case of binary classification, we had the not 5 and 5 as our classes. And in case of multi-label, we had two labels. One is large, other is odd. And we are putting these two labels on each digit. Yeah, that's right. Consider it as multiple properties, feature on an image. That's right. Thank you, Ross. Wonderful, wonderful. So should we move on? This is something interesting and great, great. All right. So now we have a further generalization of the multi-label classification, where each label could be each label, instead of being true and false, it could be multi-class. It could have different values. It can have different values. Okay, right now we only dealt with the multi-labels where we were having an array of true and false, but sometimes each label can be the multi-class. Each label could be a value, some other value, right? So multi-output classification examples are, the one which we are going to take is very strange one, is called removing noise from the images. Removing noise from the images. Okay, so what we're going to do is, first we will build our own data by putting noise into the images. We are going to put noise into the images, and then since we know the original image and we know the noisy image, we will train our classifier to clean up the image. Okay, so Gopi, you wanted to unmute?
I lost my alumni library card.
Yeah.
Yeah,
Yes, go ahead, Gopi. You wanted to say something?
yeah, sure.
I think it was by mistake. I think he wanted to mute and he unmuted. Okay. Um, all right. So what we're going to build is, we are going to build our own data set right now. What we're going to do is, we're going to make the images noisy, and then the right hand side is going to be an image and left hand side is going to be the noisy image. Okay, and then we'll train it and we will generate the clean images. Now, this would look like a regression problem, but it's not a regression problem. It is basically the classification. So it's actually, it sounds like a regression problem. And so 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 basically, let me just go back to the book, the notebook. All right, so there are going to be 784 labels, and each label is going to have multiple values from 0 to 255. It is thus an example of multi-output classification system. So let's take a look at this. We have, say, a matrix here, okay, which has so this is going to be the output, whereby each record is going to be an image, and each value is basically one label, and that value has got the values from 0 to 255. Okay, so okay, so our system will basically remove the noise from here. So let's first generate some noise. Okay, generate some noise. Okay, so what we're going to do is we are going to generate the noise like this. So here we're saying, give me a random integer between 0 to 100. Okay, and the total number of records you want is this. So total number of records we want is this, and we want this for these many columns. Okay, so this is the size of the random data we are expecting. This is total number of observations, and this is total number of features. So this by this matrix, this was 60,000 by 784, right? So this matrix contains random numbers between 0 to 100, 0 to 100, having these many records and these many columns. Okay, then what we're going to do is we are going to generate xtrain by summing up noise with this. Okay, notice that we are not going with 0 to 255, otherwise it will be a little more difficult. Okay, so here we are adding that noise. All right, then then we are generating the noise, similar noise for test data. Okay, test data, and we are generating access mod here and so on. So, and the original one, original X train without the noise, we are assigning as Y train. Okay, so X train mod contains the X train mod contains the X train plus noise, while Y train contains only X train. Okay, now let's take a look at this. So this is the kind of image that has been generated. Okay, and the original image was, what? Y test mod, right? Okay, this was the original image, so it has been made really dirty. Okay, so now if we can generate the class, the output saying that this pixel's value should be 0, this pixel's value should be this, and so on. So we are going to, based on this image, we are going to generate multi-classes for each individual. Okay, so now we will clean this image using the KNN classifier. It's an example of multi-output classification. Okay, a single label is multi-label as it has 784 classes. Okay, so this one has how many columns, as in the Y test? Okay, the Y test and X test both have the same number of columns, 784. So the number of features and the number of labels are equal, while individual label has a value which is between 0 to 255, not uh, true and false. Okay, so this is what we have, and okay. So what we have done is we have again used the KNN, K nearest neighbor classification, and here we have fit our noisy and the clean image. So once that finishes, we are calling predict on top of it. We're calling predict on top of it on this, and the clean digit looks like this. Okay, can you believe this? All right, so okay. Do you want to show quickly your screen, Kamal? I would love to see it. Is it okay? All right. Yeah, it looks a bit different. Yes. Yes, I can see that. Okay, this is interesting. Maybe if you run it again, if I run it again, maybe I'll get a little bit different one. Let me just copy paste it somewhere else. Okay. Can I just copy paste it here? All right. So that's good. That's good. Yeah, I can see. Okay, so all right. Yeah. Okay, maybe the initial image could be even different, as in the initial image could be dirtier for you, or it could be different for me. Okay. Also, we did not use a random number generator for, as in the seed for this. Okay. All right. You wanted to show something else because I haven't shared, and you want to show something else? Okay, good. So yeah, so since we have not here, right, it will generate all different kind of noise, right? Because we are not using seed here. Had we been using seed, it'll be the same noise and the resultant could be same. Okay, wonderful, wonderful. So we learned a couple of things here, and yeah, all right. Okay, so you can see that when I run it twice, okay, when we run it twice, it is going to do this. All right. A question from Noor. This is all done in 3 lines of code, but we do not know what happened behind the scenes. How can we do it in the real world projects? And yes, that's right. So we right now have not gone into the KNN algorithm. So when we here right now we are trying to learn the semantics and get ready to solve the work. And trust me, even without knowing exact details about an algorithm, you will be able to solve a lot of problems. Okay, so general strategy we will explain to you. Okay, but for now, here what we are doing is trying to predict and is trying to predict an a value out of this. It's trying to predict a class. So it has got 0 to 255 classes for each of the classes from 0 to 784. Okay. Each of the labels, there are 784 labels, and each label has got 255 classes, and it is trying to predict those values based on the input. Okay. Okay, a question from Ross. Can you output details like number of neighbors used? Of course. Okay, you can use this. So let me just see what all does it give. All right, so you can take a look at number of classes and so on. Okay, so there are quite a few classes here. Okay, let me see if it, okay, so you can see that there are 5 number of neighbors used. All right, and just a second. All right, we will go into exact algorithm maybe during once we go through our training models, which is chapter 3, which is coming up next. Okay, as we keep on going, we'll go into more details. Don't worry about exact algorithms. So I hope we were able to at least get the hang of that. Given a problem similar or on the similar lines, when we have the fixed set of output expectation, okay, we will be able to predict or classify them, right? Okay. A question from Kamal. Is my understanding right? Since the grayness of the noise added would be on an average lesser than the actual image grayness, hence they got eliminated and should not be there. Yeah. So most likely yes. Most likely yes. So it basically identified that the based on the input data, it identified that. So you can think of, imagine that we were just identifying that if first pixel is empty or not. Okay, so we're given an image, we are saying the first pixel is supposed to be empty. So it's predicting that first pixel's intensity should be this much. Okay, based on that. So first of all, it's classifying every image into that first pixel's intensity class 0 to 255 based on the data of the image, then second pixel, then third pixel, then fourth pixel, up to 784 pixels. Okay, and it's doing it for all of the images. Okay, so this opens door to many things. Okay, this opens door to many things. We could do many things with it. We could start identifying the sound, the images. We can also identify, say, visual particular signal in the data. So you should start trying out your hands with these algorithms, right? So yes, for me also, it is quite surprising that this calculation happened really quickly, and the calculation above this, it was taking just too much of time. Okay, point from Ross: the farther out from the image you go, the more likely your neighbors are weak off. I see, I see. Okay, all right. So we will discuss in more details as we go ahead. Great, great. So this is what we've done. We have been able to. All right. So we started with binary classification, and then during binary classification, we studied all the matrices, and then we did multiclass and multilabel. In case of multiclass, the understanding of the matrix is still left, the weighted one. We can take it up maybe after a while. All right. So it's still taking forever. Yeah, it's still taking forever. Okay. All right. Good. So this is what we have covered so far. We talked about binary, then we multiclass, then multilabel, then multi-output. Okay. Okay. So for questions, you can do that. All right. Should we start with training models now? This is chapter number 3. So this one would help you understand what goes underneath, and we will start with the basic one and then we will optimize upon that. Okay. Please note that a bit of theory ahead, a bit of maths is ahead, and there'll be, in this particular chapter, there will be less of examples. Okay. That's why we wanted to cover the hands-on approach first. And you can actually get a lot of work done without knowing what what is the algorithm underneath. Okay, so a lot of work can be done without having to worry about what is going on underneath. Okay, so all right, let me just give you the link to the slides. Okay, these slides are private and confidential. Please do not share them with anyone. Okay. Okay, though we plan to make them open source at later point of time after this. Okay. All right, let me just give you the permission. I think it is only shared with the team, and anyone at CloudX Lab can be. Okay, anyone with the link. All right. Okay, so here we go. Great. Are you able to access now? All right, wonderful, wonderful. So far we have seen that we were able to achieve a lot of things just by just by using the existing algorithm. And trust me, whatever we have learned so far, you can actually utilize it and uh, start competing on Kaggle or start solving the real problem. And there is a project assignment which is coming up. A musician wants to work with us for the analysis of music. If some of you are interested, I can include you. Okay. And yeah, all right. I'm not expecting any kind of money out of it. I'm doing that for okay. All right. All right. So in this case, please note that we will have to sign a non-disclosure agreement with the client, and then we'll have to work on that. Okay. So it's not Kaggle, it's a real project from somebody. Okay. So that is coming up. So I would want you guys to be involved if you are interested. Okay. Because most of you have been doing good, and yeah. So all right, all right. It's a musician. Sorry, I sound like magician. Okay, all right. It's a musician, as in the person is into composing music, and they want to analyze some kind of. They want to uh, build kind of a database of music, and for that they need help in identifying. Okay, all right. So great, wonderful. All right, Ras. Great. Ras, Noor, and yeah, Nirav. I'll have let me see how we can coordinate, and I will talk to the talk to the person, talk to the client, and would get their NDA, and get it signed. Okay, wonderful, wonderful. So a lot of such projects keep coming in, and we just need to get them executed. So we'll be involving you as we go forth. Okay, so just that when it's a production kind of work, a real-time work, there is a kind of the and confidentiality and confidentiality is required, and we also require as in the punctuality with respect to work. So that's one thing that is needed for the production kind of environment. Okay, so if I understand, okay, so I hope that'll be okay with all of you. All right, wonderful, wonderful. So yeah, all right. Yes. So there'll be a project plan. Actually, we have to come up with a plan. Okay. And that is something that would depend upon our approach to the problem. Okay. So probably I'll be discussing with him uh, in a couple of days, and then I'll keep you updated. All right. Wonderful. Wonderful to yeah, know that most of you are interested. Great. Right. Right. Okay. Great. Thank you, Noor. Is it giving good results with 125 nearest neighbors? All right, so let's get started. So just wanted to tell you that with the knowledge what we have done so far, we can actually start working on the real projects. Okay. And you'll be surprised to know that a lot of things can be done with the knowledge you have so far. We can, as of now, what we can do is we can take analogies of the work what we've done so far in the next upcoming thing. Say, for example, if you wanted to remove the noise from music, and we have, let's say, finely edited audios like studio recordings like we have, we can actually do the removal of the noise in the background, right? Based on the training data, right? So we could take many analogies with what we have done so far, and the approach we also know the end-to-end approach, and we also know the most of the how do we clean up data, load data, transform data, and everything. Okay, so we are all ready to start experimenting on the projects. Okay, so even if we are not very clear about exact approach, say KNN is taking, or exact approach SGD is taking, or say random forest is taking, but still we are able to use them and experiment with them. Even if we consider individual algorithm as black box, we are able to do a lot of things. Okay. All right. All right. Great. Now, okay. So this is what we have learned. A quick recap without knowing anything about what is going under hood. But the things that have helped us is choosing the appropriate model by as in using right training algorithm, comparing them, tuning hyperparameters, debugging the issues, and performing the error analysis. Okay. So in this session, we are going to learn internals of uh, how models are trained. We'll cover various algorithms of gradient descent, and we're going to cover the various variant of gradient descent, batch gradient descent, stochastic, and mini batch. And later, we will learn different ways to regularizing linear models, ridge regression, elastic net, and so on. Okay. Then we will learn about logistic regression, and most of the topics discussed in the chapter will also be essential in the neural net. Okay, so it's important why we have brought this in. We have realized that these the training models are quite used not only in the normal machine learning, the one that we are doing, uh, it is also applicable in the while we are training our neural net. Okay. Okay. All right. Neeraj, I did not get your question. Request you to connect with this topic and what we have learned so far. All right. On large scale of things, let me recap what we did. We learned Python, then we learned NumPy, SciPy, then we learned analytics, as in statistical inference. We learned statistical inference. We did the introduction to machine learning. Then we went ahead with end-to-end project. After that, we learned the classification, and now we are on training models. All right. All right. Now, so whatever we're going to learn is going to be having a lot of impact in most of the things that we're going to use further. Okay, these things, once you know this part, you will be able to optimize various things and think in terms of how exactly some algorithm is working. And in case it's not performing great for you, you might want to tweak things a bit. Okay. All right, so we are going to start with learning notations used in the course. These notations will help us in understanding the mathematical equations. So let's take an example of housing data set from end-to-end project for understanding the notations. Okay, so you remember this is what we have. I hope this is not washed away. Okay, all right. So you remember that what was it? All right. So here we had these features in our data set. Remember? So we had longitude, latitude, housing median age, total rooms, total bedrooms, population, so on. Right? And we had to predict the median house value, right? All right. So M is the number of instances in the training data set. So M, when you see the smaller M, there is going to be the number of instances in the training data set. So when we say M, what was the M in case of classification? The MNIST problem? Correct, correct. Okay. Then the second notation is X and the I superfix, as in, what do you call it? This superfix. Okay. There is a good term for this. There is superscript, right? Yeah, thank you. So xi is a vector of all the features excluding the label. So if we remove this value from here, okay, and the xi is going to be the ith instance in the data set. Okay, so this is going to be, this value is y superfix 1, and x, the remaining values will become x superfix 1. Okay, and so on. I mean, generally it starts from 0. It's going to be X naught and so on, right? Question from Noor. Just to clarify, features are same as attributes or fields in the table. That's right. Okay. Just in this context, remember that median house value is not a feature. Okay, not a feature. Why? Because this is something that we want to predict. Remaining things on the basis of which we are predicting are called feature, right? All right, should we take a break? It's yeah, that's right, Kamal. I in X vary from 0 to m minus 1. Good. Let's take a break from 10 minutes. All right, so I'm back. Should we start? Okay. All right, so let's start. So we were talking about notations. M is the number of instances, and X superscript I is a vector of all the features. And for example, if the first district in the dataset below has the values longitude, latitude, inhabitants, and the median income is this much. So X1 and Y1 will be X1 and Y1 will be this. Okay. So X superscript 1 is going to be this. All right. So, right, because why Y1 is there is because this is our target. This is our target value. So this is the um, something that we are trying to predict. All right. Now, the capital X is the matrix. It contains all the feature values. So X1 is a vertical one like this, right, is a column, right? And if we want to prepare a matrix of all the features from the whole data set, then that will be called capital X. Okay, that will be capital X. So X1 T, why T? Because X1 was a column and we want to convert it into a row, right? That's why we are transposing it. Okay. In NumPy, you can just say at any array, a NumPy array dot capital T, and it will transpose it the way we showed you earlier. So there is one row per instance, and ith row is equal to the transpose of xi, which is noted like this, right? This is clear to everyone. So capital X is something on which we train our algorithms. Okay, the capital X is something that we train our algorithm. Okay, now H is the system's prediction function, also called hypothesis. Okay, so once we are given this data capital X, okay, and also the small y, what we are going to do is we are going to prepare a hypothesis as what is it that how X and Y are related. Okay, what are the things that we should change in X in order to achieve some Y? Okay, that's the training we do. And once we are done with that, we can use our train model and a record from the left hand side to generate the right hand side. Okay, so this is called hypothesis. We prepare a hypothesis that maybe our left hand side and right hand side is related like this. Okay, that hypothesis is something that we try to predict. And yeah, so when we train a model using instance feature vector xi, we get predicted value y hat, we call it hat. Okay, we call it hat, and we run xi as in one of the instance we pass our feature vector xi through the hypothesis to get the predicted value. Okay, so y hat is the predicted value. Okay, so yi is the actual value. You are right, Gopi, and y hat is the predicted one. Correct. Good, good. Okay, a question from Noor. Even when we are saying there are number of features, we are training the model on these features. In reality, we are only considering only one feature. Not really, Noor. We're going to consider all of these features. We have considered in past as well, most all the features. Okay, when we were running, say, okay, so we had trained even in this case, right? Even in the housing case, we had trained our model using all the features. Okay, all right. Did I answer your question, Noor? Okay. Would you like to rephrase it? Let me try to repeat it so that maybe I get a hang of it. Even we are saying there are number of features and we are training the model on these features. In reality, we are only considering one feature. In this case, income feature to median house. Actually, in the approach we took earlier, we actually used all of these features. In the last, towards the end, while we did analyze the correlation between various values, but towards the end, finally, we actually used almost all the features to predict. Yes, Pavan? We even considered this one. Okay, thank you, Pavan. Yeah, any was I able to clear the confusion? No, please feel free to let me know. Okay. Yes. So if there any feature change, if there are features, different features, then there will be a change. Correct. Your understanding is right. All right. So this is I would request everybody to pay attention because these are the things that we would not like to. We would just like to stick to the terminology, so that we don't have to explain many things. So, all right. Although I'll try my best to be extremely simple in the approach, instead of just using X and Y all the time, we will try to be more. We'll try to keep it more, you know, more simple. We'll try to keep it simpler. Now, if the model predicts that the median housing price in the first district is this, then this is the value predicted by our model, then our y hat 1 is equals to this one. Okay. And the prediction error for this district is this much. This is called prediction error. Okay. RMSE is the cost function. So given the hypothesis and given the actual data, okay, we would be able to predict y values and we would be able to compare the predicted and these values. Okay. So RMSE is the cost function measured on the set of example using hypothesis. Okay, so root mean square error is what it means. In general, we use the lower italic font for scalar values such as m or yi. Okay, scalar value as in individual value. Okay, individual value will be representing by y. Okay, and lowercase bold vectors are going to be lowercase bold will be used for vectors. This is a list of values. Xi is the ith ith data set, ith record, or ith set of values. So this is a list of values, list of scalars, and that's why we are going to use it bold. Yeah, this is ith row. Okay. A question from Gopi, is cost function same as loss and penalty? The cost function is, yes, is basically similar to loss and penalty. Okay, so cost function is equal to penalty, and the loss is the individual derivative. So let me put it this way. We will the cost function, overall cost function, has two aspects in it. One is called loss, other is called penalty. Okay, we'll go into more details about this. All right. So uppercase, this is important, uppercase bold font for metrics such as this. Okay, that's why the right hand side y is smaller, while left hand side x is capital. Okay, so let me go back here. So this is a feature vector. So this is represented as bold y. This is represented as bold y, while this whole matrix, including this, is capital X. Okay. So that's something we are going to use as such. Right. Now, let's understand what does it mean by regression, linear regression. Okay, I hope this is clear. So M is for number of instances. The superscript is for extracting ith value. Okay, and so on. The subscript we'll talk about soon. Subscript we'll be talking when we talk about summations. We'll use subscript when we are, let's say, iterating over this, and we want to say it's a summation of all the values in X. Then we'll say J here, and then we'll sum it up. Okay. Yeah. A question from Nirav is, how did we get yi? Yi is basically, first yi is the actual value. Okay, yi is the actual value. Y hat is the predicted value. All right. Okay. The notation with the subscript is going to be for iterations. Okay. How did we get the predicted value? Yeah. Earlier, this is basically, we haven't done this now. We have just taken it from our example. Okay. Okay. The feature number is denoted by xi. Sorry. Okay, let me go back what it means. I think feature value is by subscript only. Okay. All right. Now let's use the whatever symbols we have used, and we will learn more symbols as we go ahead now. For example, thetas and other things we will learn as we go ahead now. Okay, so a very simple example, let's take a case of linear regression. Okay, and you will get used to these symbols as we are moving more and more ahead. Yes, I think n is used for number of features. Yeah. Okay, so let's take a look at a simple linear regression model of life satisfaction versus GDP per capita. Okay, so here there is a graph plotted between GDP per capita and life satisfaction. Okay, as the GDP per capita is increasing, the life satisfaction is also increasing. Okay, so life satisfaction is equal to theta 0 plus theta 1 into GDP per capita. Here, this is an assumption. We are thinking that there is a line that is going through it. So our hypothesis right now is this. Okay, this is linear regression. Okay, in other words, we were given some data and we thought that one line should fit it. Okay, so to predict this line, we need two values, theta 0 and theta 1. Okay, so theta is the order of polynomial, you can say that. In this case, if it's a straight line, we can also say theta 0 is the distance from the center and theta 1 is the slope. All right, that's right, Binta, you are right. Okay, so this is called linear regression. Linear regression is all about drawing a line through set of points. This is the most basic form of things. If I have few data records like 3 or 4, I can actually do that. Say if you have 2 records, right? Uh, I can actually do that with pen and paper, but still it'll take a long time. It won't take too much time to actually draw a line through 2 points, but it might take a bit of more time to compute a line which goes through 3 points. Okay, so yeah. So this is a linear regression. Linear regression is the most simple and the oldest form of predictions. Okay, this is the most oldest form of predicting the values in future. We used to draw on the chart paper, draw these data points on the chart paper, and try to draw the line that is passing through them. Okay, and measure that how closest the new line is to all the data points. Okay, so okay, so here, all right, so let us say after a while we realize that the life satisfaction equals this much plus this much into GDP per capita, then this is our final equation. Okay, and so quick question to all, what does this equation mean? Life satisfaction equals theta 0 plus theta 1 into GDP per capita. Correct. It's a simple linear relationship, meaning if you multiply GDP by something and add it with something, and we should get approximate life satisfaction value. It's a hypothesis, okay? It's a hypothesis, and we need to find these values to make this hypothesis predict our values. Okay, this is our edge. Okay, okay, by plugging in various values, we can always calculate this. Okay, so the general equation of line looks like this. Okay, the general equation of line used to be this. We draw a line here and we call it y equals mx plus c. M is the slope of the line. M is the slope of this line. How much slanting is the line? M is that measure of slope. Basically, M is a function of this angle. The more is the angle, the more is the slope, and less is the angle, less is the slope. So y equals x into slope plus c. C is this distance. If you put x equals to 0, where does this line meet the y-axis? We also call it y-intercept. So this is how we used to draw it. Now we are calling c as theta 0 and m as theta 1. Okay, m as theta 1 and slope as theta 1 and intercept as theta 0. Okay, this is also called y-intercept. Okay, so what if y-intercept is 0? Quickly, if the y-intercept is 0, what will happen? If this is 0, y-intercept is 0, which is c is 0, it will pass through the origin, right? If slope is 0, the m is 0, then it will be basically a horizontal line. Okay, so it will pass through the origin. Okay, good, very good. Now let's go back to the end-to-end project. If we build the model of predicting houses using below attribute, let's say longitude, latitude, inhabitants, and median income, then, and we are thinking that it's a linear regression. We are assuming that it's a linear regression, then our predicted house will be some kind of this, right? If there are more variables, So, our predicted price is a function of theta 0 plus theta 1 plus theta 1 into longitude. This is the variable, and these are the weights. We call them weights. Okay, so this is 0th weight, this is first weight, the second weight, and so on, right? All right. So our predicted housing price for linear regression having multiple variables, this was with one variable. There was only one feature in this case. In this case, there was only one feature. Here, there are multiple features. Okay. We have longitude, latitude, inhabitants, median income, and so on. Okay. So these are the various weights. So question from Noor. So the features which have linear relationship would be considered. No, so actually right now we are just thinking, we've just picked up 4 variables. We're just thinking that our relationship is linear. Okay, it could be complex, it could be anything. Okay. Okay, a question from Nirav. So what is the theta value, theta 1 value here? That's what we are going to, as we train our model, these values is what we guess. These values is what we call our learning, or you can say our model. Okay, this is our, basically these thetas become our model. When we train something, the algorithm basically finds the values of these thetas. All right, sometimes this theta 0, theta 0 is also called bias or intercept. Okay, so this is the weight of first feature, longitude. This is the weight of latitude, this is the weight of inhabitants, this is the weight of median income. Okay. So the general equation, if we consider our overall scenario, if we are considering our overall scenario as linear regression, this is how it is going to go. Okay. I hope everybody is okay. Not going to sleep, because the moment we see these symbols and we are not used to it, we kind of feel sleepy. Okay. And okay, a question from Node. What I'm trying to ask is, if any of the features in data set doesn't have any relationship with the expected value, then changing that feature will simply ignore. No, actually, we are not going to ignore it. We are just going to approximate it. Okay. Even if things look like non-linear, still you can some way do approximation. Okay. Still you can do approximation. All right. So this is the general equation. So here, what you see is y hat is the predicted value, and this is the value. So you are right, Pawan. So subscript is what we're going to use for individual value in the x vector. Okay. So this is how it is. All right. Theta 0 plus theta 1 x1 plus theta 2 x2 and so on. Given this, these values, theta 0, theta 1, x1, x2, x3, no, sorry, given all these thetas, we can always predict y based on x's. Okay, so xi is the ith feature value. Theta 0 is constant, also known as bias, and theta j, the j with the superscript, is the model parameter, including the bias term theta naught. Okay. So this is something that we try to guess. What are those values of thetas for which our y will be really close to the actual y. Y hat will be close to the actual y. So we try to kind of find out the value of thetas in order to minimize the distance between y hat and original y. Okay. A question from Gopi. If there is a mix of linear and nonlinear, we could have said this. Yes, but yeah, but we do not know that part. We do not know that part. All right. So bias term is very, very important. Bias term kind of makes a lot of difference in the overall values, right? While the change in slope might have a little difference, but bias term has a huge impact. Okay. So for example, let's say this data is the data is plotted like this. If we have bias term at 0, our line will be parallel to this. So there is a huge loss, huge difference from the original value. With bias term, our line will go through this. So bias term is important. Bias term is very important. Okay. So bias term does not depend on any feature, right? Adding a bias weight allows the algorithm to easily fit data that does not pass through origin. Okay. In other words, this is how it looks like. In other words, this is how it looks like. So y hat equals to hypothesis. Here we are putting theta as subscript, meaning hypothesis is a function of theta. Okay. This is for linear regression. And so H theta is basically for linear regression or regression. And here X is the input vector. the feature vector. So this is our general equation. So theta is the model parameter, okay, containing all the bias terms. Sorry. Um, yeah. So theta collectively, when all thetas are together, then theta is a model parameter vector containing all the bias terms starting with theta 0. Okay. Let me reiterate the entire thing. So yeah. Okay. So right. So theta is collection of, theta is a vector, right? Theta 1, theta 2, theta 3, theta 4, up to theta n. And theta naught is the bias term, okay? And when we transpose it, as in we make it from vertical, we make it horizontal, right? So theta is kind of a vertical values, and by using theta t, we are making it horizontal and multiplying it by x, okay? Multiplying it by x, and that's where this equation comes from, okay? That this is something that would come in. Okay, let me say it again. So so theta is basically, you can think of theta as this is uh, theta 0, and this is theta 1, this is theta 2, this is theta 3, and this is overall theta. Okay, so theta is equal to this. Okay, and this one, so this one, when we say, yes, Gopi, you have to say something. Yes, Gopi, you have to say something. Actually, I think it was unmuted by mistake, so I have muted. Okay, now why we are transposing it? Because we want to make it horizontal, and when we do the transpose here, when we do the transpose, this would be like this. Okay, I think Gopi, you are again unmuted. Theta 1, theta 2, right? This is how it's going to be. So when we transpose these thetas, they'll become horizontal, right? They'll become horizontal. And that's why we always write theta t, okay? So if you multiply these, let me just draw thetas. Theta 0, theta 1, theta 2, okay? And we have here x1, x2, and x3, and so on, right? So this would lead to, when we multiply these things, when we multiply two matrices, right? How we used to multiply? We used to take a row like here and multiply it with the column, correct? When we do the scalar multiplication, so it will result in our this equation. Okay, it'll result in this equation. Is it clear to you why we have said theta t dot x? All right. So this one is, I think there is a mistake in this one. It should be theta 0 followed by theta 1 and theta 2. Okay. All right. No, it's going to be, yeah, would have theta 0 as well. Okay, this will have theta 0 as well. Okay. Now, the capital X is the instance feature vector containing x naught to xn, and x naught is always equal to 1. So we basically, in order to make this, had there been no 1 right here, no 1, what would have happened? Theta 0 would multiply with x1, theta 1 will multiply with x2, theta 2 will multiply with x3. So how many of you remember the matrix multiplications? Nobody? So we take each row, multiply it with each column, and that's how we multiply matrix. So in order to handle multiple records, it's always easier to represent your data as table, correct? And when your data is in the tabular form, meaning it's plural data, and everything that we studied in algebra becomes linear algebra, because we need to multiply two values, and those values are list of values, and hence the whole sequence of things convert into linear algebra. So whenever we are multiplying, the way we have been doing earlier also, whatever operation we did on numpy, we were operating on the whole list of things, whole list of numbers, not list of things. We were multiplying, say, when we compared, when we calculated not 5, all we did was we operated on the entire vector and said not 5, right? Therefore, whenever we are dealing with the data set, we will be using mostly the vectors, and therefore the vector algebra or linear algebra, or we also call it the matrix multiplication or matrix um, matrix problems, or sometimes some of these are also called determinants, as we will see ahead. So whenever we are moving from one individual values to the list of values, most of the things that we learned have to be changed, have to be changed to multiple records. Okay, yeah, this is a dot product. Okay, so this is dot product. We are going to multiply this with this. Okay, so the whole this whole multiplication, this mechanism of multiplying, is very easily represented as dot. Okay, and that's why it is so theta t into dot. Okay, and we understand why we have introduced 1 here, though there was no 1 in our feature vector. So this is longitude, latitude, housing value, and the population, and so on. These are those parameters. While how these are related to the output, these numbers are calculated as part of the model, and that's what it is. Okay. A question from Gopi: why is capital X a feature vector here, and was a matrix in notation slide? Okay, here it's a small x, if you see. Okay, here it's a small x, right? And capital X contains all of these x's. Okay, so let me just change it. That's a good point. Thank you. All right. So h naught is our hypothesis function using the model parameters at theta. H naught fits the model and calculates the weight. So basically, this is the role. This is the role of our machine learning to find out the hypothesis function and and calculate these weights. So a point from Pavan, column matrix is also called a vector. You can say that, yes. Now, question is, how do we train it? Okay. All right. So Kamal, that might require no. So yeah. So in those cases, that one has been moved as a bias outside. Okay. That one has been moved as a bias outside. Okay. So that becomes easier because B is absorbed into the matrix, right? Now, question is, we all agreed that, yeah, we need to find these thetas, we need to start predicting. Now, question is, how do we find the values of thetas? Given X and given Y's, how do we find out the value of thetas, which will start predicting the values which are closer to the original? Okay, so how do we train the model? Training the model means setting its parameters so that model fits best the training set. For this purpose, we need a measure of how well or poorly the model fitting our training data. As we have seen, as we've seen in the end-to-end project, common performance measures of regression model is root mean square error, mean square error, and so on, right? So what we are going to do is we are going to find the values of thetas which are very closer to our original value. And how do we define closer? By using either the root mean square error or using the mean square error. So we will minimize these errors in order to come up with best possible solution. Okay. So the things that we learned in our childhood where we were finding the value of X and Y, those were basically in the algebra sessions, those X and Y were great if there was no approximation involved. Here, here in the real life, a lot of approximation is involved. Therefore, that mechanism of equation solving may not always yield a great output. Okay, so we basically have to find this we have to find the thetas such that our overall error, or we call it cost function minimization. All right. So we will be using MSE, mean square error, for training the model in this session. Why MSE? Why not root mean square error? Quickly. Instead of root mean square error, we are using mean square error. Why? Yes, it is simple because we don't have to compute the under root, because square root computation takes a lot of time, right? If you have to write the square root function by yourself, how would you compute a square root? It's actually quite tricky thing. Okay, computing square root. So RMSE and MSE both are simple positive functions. Both are positive, MSE as well as square root. Okay, so we don't need to compute the square root. We can just get with the MSE, and that's good enough. Okay. The function that minimizes MSE also minimizes the square root. So it doesn't matter whether we use MSE or root mean square error. Okay. So let's just do a quick recap of MSE. The way we computed MSE was, let's say we want to predict house value based on the area in its square root. We use univariate linear regression. Since there is only one feature, house area, we could draw the line like this. We have house area, house value, we draw a line like this. We have W0 and W1. Okay, now we basically drew a line, computed our predicted value. Predicted value is the ones that are lying on this line, and we computed this delta. This is y hat and this is y. So when we subtract these two, we get the error, right? So this is the error. This is what we predicted, and this is what was original. This is what we predicted. This is what was original, and so on. So we are trying to draw a line to minimize this error. Okay, so this is the error. This is the individual error. Then what we do is we sum up these errors, this plus this, square of this, square of this, square of this, and so on. So we summed up all of these, divide by m, which is total number of instances, so that the order of the resultant remains in the same scale as the actual error. Okay, so mean square error and the individual error are on the same scale. That's why we divide by m. While training the model, we have to find the value of theta that minimizes MSE. Okay, so finally the MSE is, we sum up for every record. Remember what was m? For every record, we have to compute theta. Sorry, for the assumed value of thetas, we multiplied by xi the the ith feature vector. So, and we subtract this for each of the record. Each of the record, we are going to compute this. Okay, and then we divide by m. Okay, so this is our predicted value, right? This is our predicted value in case of linear regression. And this is our actual value. So y hat minus y I square, that's our individual records error, individual predictions values error. And then we do that for all m records. That's our mean square error. Okay. Is it same page? Is it okay, or should I move a bit faster? So sigma means that we are summing up all the values. Okay, sigma means we are summing up, we are putting, it's like for loop. We are going from 1 to m, and we are summing up these values. That's what it is. Okay. All right. So xi is the vector of all feature value of ith instance in the data set. Yi is its label, the desired output value for that instance. Okay. So this is how it looks like. Okay. So y, if you see, is a italic. That means it's a scalar value. Yi is a scalar value, while x, which is bold, it is basically a vector, and we are multiplying theta, which is also bold and is a vector. We are multiplying these two, subtracting by y, and squaring it. That's the function of mean square error. Okay, so here is an example of xi and y1. Now, while training models, we have to find theta which minimizes error. Error could be RMSE or error could be MSE. Okay, so the overall idea is to find thetas that minimize the root mean square value. Okay, in case of linear regression. So let us understand how the training of linear regression model done internally. There are two approaches to train the linear regression. One is normal equation, the closed form. Other is gradient descent, iterative optimization approach. Okay, so okay, so this is basically the classic form of equation. We will talk about this now. There are two ways to find thetas. One is solving n number of linear equations, to find theta. Remember how we used to solve linear equations? We used to cancel thetas from here and there. So we eliminate variables and then we find some value. So this normal equation is similar to that one, just that it does the approximation. Okay, so there are many algorithms to solve normal equation, and even the best one is of O(n) cube. Okay, I'll just talk about O(n) cube. Okay, so yeah, it's kind of solving simultaneous equations, and okay, so uh, you remember that if we had like x and y, and there are two equations, we'll cancel y, we'll keep x, and we'll compute that. That is one way of computation. Or there is something called normal equation, which does the same thing, just that it does the approximation there. So given n number of equations, it can find those n values. So that used to be called normal or closed form equation. Okay. The second way is assume thetas and then keep on trying again and again by increasing or decreasing thetas. And that's called iterative approach. That's called iterative approach. Since iterative approach could be could take forever, therefore there are optimizations to this iterative approach. One of those that optimization is the gradient descent. The gradient descent is basically an iterative approach. We are writing a huge for loop which is going to keep on changing all thetas and keep on trying to minimize the error. Okay, it will basically try all possible lines through these ones, and then go to the one which is giving the minimum error. It just do it using a very clever or greedy approach, and that's what we are going to discuss. The normal equation is something which we have here. So here, when we write it mathematically, this is how it looks like. This is how it looks like. So we are saying, so we said, when we try to solve this equation, let me go back here. Yeah, if we try to solve this, what we're going to do is we're going to so this theta t dot x equals to y. So if theta t we have to take if we have to take x to the other side, is going to be like this. Is going to be, if we take x to the other side, this is what it will become. It'll become xt into x, the inverse of it, and then multiplying the transpose dot y. This is called closed form equation to solve thetas. This basically finds the value of thetas that are based on n number of simultaneous equation. Okay, based on n number of simultaneous equation, it computes the thetas. Okay, so x is our training data set. Okay, and y is our target vector, and theta is what we are trying to find out. Okay, so let's try to see the normal equation, if it is working or not. Okay, and I hope, let me just go back here. Good, good question, Pavan. Okay, right, this is where we are. So here is some part which is will be used again and again. This is for pretty figures. We are setting the random seed, and we are also importing, doing the various import, and this is for Python 2 and Python 3. Okay, so that if even if you are running this in Python 2, it should mostly work. Okay, save figure saves the output of this into your project directory, which is current one in a chapter ID like this. Okay, so these are common utility functions so that we can call save figure, and whenever we are plotting, it would become little pretty. So this is better. All right, now let's see. We're generating some kind of noise here. Okay, we are generating noise here, and then we are adding that noise to a linear equation. So here we are saying y equals 3x 3 plus x. So let me also show you how it looks without any noise. Okay, all right, let me just do these. Okay, so this is our y, and then we are plotting. Okay, what did I do? Let me just remove this part. See, so what we have done here is basically what I want to show you is it's a linear line that we have just done. So we generated some values of x. We generated some values of y based on x, multiplying x with 3, adding 4, right? And then we plotted x and y. Okay, so this looks like a nice line, right? So further, yeah. So noise is same as jitter. Basically here we are just adding some random numbers. Okay. When random numbers is, we call it noise. And noise and jitter. Jitter is generally considered a spike, but yeah. So it all depends in the context we are using those words. All right. So now we basically generating list of values x, and then we are generating list of values y, and we are adding some amount of noise here. Okay, some amount of noise. Okay, that means when we plot that one, okay, let me just move this up. Can I move this up? I doubt. Okay, so let me just delete it. I don't think it's required. Okay, so when we plot this, this is how it looks like. See that? This is how it looks like. And this is actually something we have to be cautious here, because that random number, if I generate again, it is going to be different. Okay, I'll show you. It's going to be different. You see that? This is definitely, you'll notice that it is definitely different. Yeah, we need seed, and we need to do the seed again and again. That's the point I'm trying to make. So let's say here we generate it again. Okay, do you see the difference? Right? This is different from this. So this seed, which we have set once, we might have to set it multiple times. Okay, we might have to set it multiple times. Okay, now when I plot it here, this time both are same, correct? So now I hope you got the idea that if you don't fix the seed before every random number generation, it will basically take some other seed, okay, and hence generate a different random number. All right, so good. So this is the data that we have generated. Now we want to find out a line which would fit this, And how do we do that? Here here is our normal equation. We are saying xb equals to this. What is it? We are concatenating 1 with x. Remember we talked about putting 1 before x. So we are adding ones to each of x value. Okay. So let me show you. This was x. This is the data we have already, right? X and Y is the data we already have. So what we did was to each of the record X, we are adding one more value, right? So because here there's only one value, so it's going to be one this record, then in the second row will be 1 comma this record, and so on. So if effectively your xb will have 1 and x. Okay. So let's say x is 0.25, 0.5, and so on. So this xb, let me actually show you what is xb. Okay, so okay, so xb is this. Xb is 1 this, 1 this, and so on. Okay, I hope this is clear. If you have x here, so you can see that capital X 0.749 and so on, and here it's 1 comma 0.749, right? So we basically, first of all, we are generating this, which has 1 appended to each of x, correct? Now this is the linear what do you say, normal equation. Okay, normal equation has what all things? Normal equation has this part. So we have to find this inverse into xt into y. Okay, so the inverse of what? Transpose of your x, correct? Transpose of your x here into capital X, into as in dot product with capital X, correct? Dot, we are saying again, we are calling the dot function, the dot product on transpose of this. So the inverse multiplied with dot multiplied with x transpose into y. Okay, that's what we have done. All right. So I think this would be clear to you. So when we do that, this is the theta best we got. Okay. All right, Gopi. So Gopi's question is, if everyone doesn't mind, shall we wrap up at the next heading of the notebook? Yes, that's not an issue. We just have 10 minutes left. Is that what your point is? Okay. All right, no worries. So we'll just, if you have questions, feel free to ask. I would love to answer that. Okay. So are you able to run this? I would say that let's run it. All we are trying to do is a very, very simple thing. We first generated this data. Okay, it's artificial data that is a slight deviation from our linear equation, right? The linear equation will look like a simple line, and we have just put a noise in it. Okay, now we are using this standard equation. Right now we are not going into this derivation of this one. Here we are first computing x multiplied with transpose of x dot x transpose of this, x transpose dot product with x. Then we are computing the inverse. Again, inverse computation of inverse is a very hard thing. Okay, computation of inverse is actually very hard thing. It is as hard as finding the solution for n linear equations. Okay, and then we are saying dot product here, and then we are saying dot here. Okay, so using this formula, we directly get the values of theta 0 and theta 1. We got the equation of the line that is passing through these records using the normal equation. Okay, using the normal equation, we found the best theta. Okay, and if you want to do the predictions for say 0 and 2, okay, we can simply do that. Okay, simply do that using here. Okay, how do we do that? We multiply theta with this. Okay, all right. What does mean by NP1s? What it generates is it generates the one having 2 rows and 1 column. Okay, so it's going to generate, I'll just show you this. I think this should answer your question. Okay, you see that? Unit matrix, correct. Okay, so let me just print each and everything. Print x underscore new. Then we have print x new b. Okay, and then we have print y predict. So this was our input variable, the value of x for which we want to do the prediction based on the model that we have generated. This is our model. The values of the slope and intercept is our model. So using this formula, given our data x and y, we computed thetas, and these are the thetas using the normal equation. Okay, so we got these thetas, and then we here said here we are trying to generate the value for 2 and 1. Okay, value for 2 and 1. 2 and 1, it is going to be this approximately here. Let me see, what did we feed? X new is how much? 0 and 2, right? Sorry, 0 and 2. We wanted to find out the value for 0 and 2, the two extreme. So the G for value 0, it should be somewhere here, and for 2, it should be somewhere here, correct? So that's what we're trying to see if it is working fine or not. And so what we did was, this is our the value that we want to find out. Then we added 1 to it. As in, instead of saying 0, 2, we said 1 and 2, and then we did the dot product, as in, to this matrix, we multiplied thetas, okay? We multiplied theta, so this into theta, okay? So that it becomes theta 0, so it'll be C plus mx, this is x, and so on, okay? Let me just put it this way from here. All right, I hope I'll be able to do it from here. Maybe clear here. Okay, so if we have this, and what was our what did we predict? These were the things that we predicted, right? So basically, this is our this is the value that we want to predict for. Okay, and these were the theta. So all we did was we did a dot product. Okay, what it means is this. What it means is this into this. Okay, so if this is our C, if this is our C, the first one, and this is our M, it's going to be, the value we are going to get is C plus M into 0. Okay, so it'll be equal to 3.7 something, correct? Is that what we're getting, or it's the opposite? Yeah, 3.7, and then the second row will be multiplied with again the same one. So the next value is going to be 1 into 3.7 plus 3.2 into 2, correct? So this is the value, okay? And the prediction is 10.10. All right, so it's extremely simple thing. All we did was, given this data, we used the standard equation to find out the line. And how do we define line? Using C and M, using the intercept and other value, intercept and the slope, or theta 0 and theta 1. Those are the various names for the same thing. So we generated this line. Now, given this line and given X values, we want to find out the Y values at that point of time. And once we do that, okay, once we do that for all the X values, we will be able to plot, the line that we have predicted, okay? Question from Bintao, what is the purpose of random 100, 1? So here we are generating a vector having 100 values, okay? And go up. Yeah, here, this is the one you're talking about, right? Let's see. So it basically generates the 100 values, random 100 values, having one column, okay? So here, what we are trying to do is, we are trying to, here as well the same thing, here we're trying to generate 100 numbers, with one column. So these are the random X values. And instead of having just the straight linear regression, straight linear relationship, we are having some random data. Okay, it's very much similar to the real world observations, because there's always the noise, there's always the things are far away from the reality. Okay, so that's why we, instead of it being all of these being very in the straight line, there's a noise. Okay, had there been no noise, you can actually calculate the line in just 2 data points, right? The line in just 2 data points. All right, so the name of the notebook is Training Linear Models. Okay, so get used to it. This is going to be quite used. Even this normal equation will be used a couple of times, but not more than that. Okay, so for most of the mathematical formulas, we will try to do in NumPy, so that we can see the practical implication of the same thing, and we will not be afraid of the formulas. Okay. A question from Pawan, is linear regression being used in real project? It does actually. You will be amazed to know that in a lot of cases, you can actually get most of the work done in linear. But trust me, most of the project, when you do, you start from linear regression and then you move on to the others. Okay. All right. Suggestion from Noor. I think a bit of refreshing linear algebra will help. Okay, so right now what I would say is, whatever we are doing in the class, try doing it by yourself. Okay, try questioning every statement. Why are we doing this? Then you will get a very much clarity, and then we can have a more fruitful discussion in that dimension. Okay, so go through whatever we have studied today, and we are basically done using this. Okay. This is what we have talked about. All right. Great. I look forward to see you next week. Okay. A question from Bintao. Is there a limit requirement of min-max of these 100 numbers? So these 100 random numbers are basically decimal numbers between 0 to 1. Okay. Why we are using 100? Because why we are using 100 in the noise? Because our X has 100 rows. Okay. Our X has 100 rows. That's why we are using 100 here again. And the min-max is 0 to 1 in these random numbers. Okay. What is the function? And since these values are lesser than our right, the overall values here, therefore this noise will not change the meaning of the graph. Okay. If we had like divide by 2, the equation will be far more closer to the original. Okay. Now, a question from Nirav, question from Binta. What is the function of these $2 here? Yeah. So here we basically putting the value of this value of dollar value of X underscore 1. Right. Let me just show you. Where are we? We're saying put X label here. Okay. This, I think this is the one, X1, and put Y label Y dollar. Okay. And okay, great. So yeah, basically this is the way you generally put the labels on the chart. All right, this is the way you put the label on the chart. Let me just try putting something like this now. Yeah, I think it's italics. The underscore means as you know, the subscript, right? The underscore means subscript and dollar means bold. Okay, that's what it means. Yeah, thank you. Okay, good. Question from suggestion from Noor is there may be some sort of animation for linear solving out on the web. So actually what Ross is suggesting is maybe there are these small YouTube videos which have the animation regarding linear equations. I can actually suggest some of them. Okay, let me suggest some of them. I have found some of them really useful. Okay, or I can take a separate session also if some of you want a quick one. Okay, and Noor suggest okay. Answer from Noor is, I was thinking of creating one myself. Probably one has to learn Django in order to do that in Python. That will really help to understand this. Okay. Right, right. Or maybe a mobile app would do. Maybe you can do a mobile app that would be easier for easier adoption. Okay. All right, because Django doesn't do the animation, it'll just give you the website and things like that. Okay. Easier would be doing the mobile app. All right. So great. All right. I'll see you next Saturday, Sunday. Thank you, everyone. Okay, I will be committing these scripts. I think, should I commit these scripts? I think I should. Okay. So this is the command that I'm using, but since nobody has made modifications to it. Therefore, this is completely okay. If you are going to make a lot of modifications, I would suggest that just copy this notebook to another file and keep on making modifications there. And later on, you can generally merge the two. But merging the notebook is really hard because it's a huge JSON object. So merging notebooks is a bit harder. All right. So is that the question you are asking, Binta? All right, great. Great set of questions. I thoroughly enjoyed session. I look forward to see you next week. Bye-bye. Have a good day. All right, sure. Let me plan, Noor.